Hello and welcome to this Fundamentals of Zero Knowledge Proofs video where we will discuss what zero knowledge proofs are from a high level. So before we start, I just want to explain to you that you can also go watch this course over on Cyfrin Updraft, which I have linked down below. Cyfrin Updraft is a completely free educational platform for developers and Web3 professionals to be able to understand everything that you need to know about blockchains, zero knowledge proofs, DeFi, and so much more. Cyfrin Updraft is really cool for 3 reasons. Number 1, it's modular. So each of the lessons is broken down into videos, which are much shorter, so it's easier to come back to and save your place if you want to go have a break. Have you ever been on YouTube where you've gone away from a video or you've wanted to go back and rewatch something and you've forgotten or it hasn't saved the place that you were previously at? Instead of that, you can just remember the name of the lesson that you were on, and also Cyfrin Updraft will record your progress. The second reason, which in my opinion is the biggest reason, is that we have quizzes. Every couple of lessons, you will have these quizzes created by the Cyfrin Updraft team to test your knowledge, and it will really help solidify things. The third reason is that we have written lessons associated with the video lessons. So if you later want to come back and see what something that you learnt was without having to rewatch the video, then you can read the written lessons, or if you prefer to read knowledge rather than watch a video, then you can do so. We also now have a search bar if you just want to quickly search some information. So if you want to try it out and have the really cool Cyfrin Updraft experience, then click the link down below. It is completely free. You will be required to sign up for a profile where you can just log in with Google or with your wallet or your email address or whatever you choose, but it is completely free. With that said, let's continue on with the video and I'll stop rambling. Hello and welcome to the newest course on Cyfrin Updraft, ZK Fundamentals, or how I like to call it, ZK Fundies. This is going to be an extremely exciting course, so get ready. I hope you have a snack. I hope you have some water because this is going to be a great one. It's a non-technical course. I'm going to walk you through a little bit in this lesson about what the course is about, who's it for, what are the prerequisites, so that you're all set up and ready to get started. This course is only about an hour long, so you won't need too many breaks. If you want to take breaks, of course, take them. But if you want to do it all in one go, this course is short enough that you can just do that. The thing I will note is that it is extremely knowledge packed. It's quite dense with knowledge. So if you want to go away, do some extra research, take some time to let the knowledge solidify, then please feel free to do so. If you don't understand everything the first time, that is completely normal. This knowledge took me a long time to get my head around, because there isn't too much information out there that is complete and actually tells you what zero knowledge proofs actually are and how they actually work. There's a lot of assumed knowledge. Anyway, I'm going to try and make this lesson as unrambly as possible. That is extremely difficult for me because I am a rambly person. So let's get started. So who is this course for? This course is for everyone and anyone. Anyone wanting to learn about zero knowledge proofs. It's for developers, non-technical people, BD, sales, marketing, aspiring ZK developers, people who already are developers. Maybe you're a Solidity software engineer or you're a Python engineer and you just want to know a little bit more about zero knowledge proofs. If you know absolutely nothing about zero knowledge proofs and you want to get started, then this is 100% the right place for you because we assume that you know nothing. So as I said, this course assumes no prior knowledge of zero knowledge proofs. We're not really going to go into the math and we're not going to be doing any programming. There aren't really any prerequisites. However, I will assume that you have taken the blockchain basics course. If you haven't taken the blockchain basics course, then I will assume that you know what a blockchain is from a high level, how it works, such as hashing, things like that. The fact that blockchains are transparent and immutable. So if those things don't really mean anything to you, then I encourage you to go back and take that blockchain basics course. But there is no programming required. So you can just get started straight away as long as you know high level what a blockchain is. So why should you take this course? Why even bother at all? So zero knowledge proofs are the future. Because blockchains are inherently transparent by design, we need to be able to build privacy into systems so that everyone can't see everything at all times. There might be instances in which we want privacy, which we will be going into in the course in a second. And in order to be able to build privacy into blockchain systems, we need a host of people who understand the fundamentals. And this is because we need people who can build cool projects and tech. We need people to audit that tech. We need people to promote and market the tech, sell the tech, etc. We need all roles to be skilled up enough to be able to understand zero knowledge proofs to be able to fill these roles. So this course will hopefully equip you with the fundamentals in order to be able to get a job involving zero knowledge proofs or to expand your skill set. So what will you learn? This course is kind of like the zero knowledge proof equivalent of blockchain basics. So in blockchain basics, we covered from a high level, a non-technical overview of what blockchains are, how they work, what smart contracts are, etc. This is kind of like what zero-knowledge proofs are, how zero-knowledge proof systems work from a high level without going into any of the nitty-gritty details, without going into any of the scary math, without having to do any programming. So we'll cover what they're used for, obviously what they are, the types of zero-knowledge proofs, the terminology associated with zero-knowledge proof systems, and the foundations to start learning more. So in the future, you might be able to learn how to build zero-knowledge proof systems with code and how the math actually works. So who the heck even am I? Who am I? My name is Kieran Nightingale, and this is my formal introduction. I'm a lead instructor at Cyfrin Updraft. I have left my social links here because I also do some YouTube tutorials. You might be able to see some sneak peeks over there if you go and follow. And those are my handles on Twitter. I don't have the E at the end, so it's just Kieran Nightingale because it didn't fit. But otherwise, most places I'm just Kieran Nightingale with no spaces, no dots, no nothing. And I've built more than 10 hours of content on Cyfrin Updraft, including some cryptography content such as Merkle trees in the Advanced Foundry course. And I also did some lessons in the Blockchain Basics course. I thought I would add here that I'm a physics grad at the University of Bath. I feel like this is just to give me some more credentials as to why I can talk about cryptography things like zero-knowledge proofs. But it's also just a fun fact about me. I also love to run and gym. And I also do a little bit of painting in my free time. Not that anyone asked. For this course, you will need to be using this GitHub repo to be able to navigate around the course. So in this repo, you will have all of the necessary links. You'll see some resources for this course, such as how to find Cyfrin Updraft if you're watching this on YouTube, and a list of all of the different lessons with some helpful links like helpful blog posts, etc. The other thing I have included here is some AI agents. Now, as I said, this content is a little bit complex. We're not going to go into the nitty-gritty details, but some things might seem a little bit abstract to you. So I encourage you to chat, pun not intended, with AI such as ChatGPT, Find. I really like Claude. But any of these AI agents are going to be great at explaining the concepts to you. So if you don't understand anything, the best thing you can do is just chuck your question into one of these AIs and it will give you a fantastic answer. In most instances. The other thing you can do is go to the Cryptography Stack Exchange, and this will be a great place for you to ask technical questions about zero-knowledge proofs and cryptography in general. And then we have the GitHub discussions tab, as with all the other courses, on Cyfrin Updraft, where you can ask questions where I or someone from the Cyfrin team can answer your question directly. But make sure that you have asked your question to AI first, or possibly made a question on Cryptography Stack Exchange. So with all of that said, let's finally get into it and learn what the heck even are zero-knowledge proofs. What if I could tell you that I could solve a Rubik's Cube without showing you the solved cube? Impossible? Not with zero-knowledge proofs. They are the mathematical equivalent of proving you know a secret without actually having to reveal it.
Wow!
Welcome to our journey into zero-knowledge proofs. Today, we are going to be diving into, in my opinion, one of cryptography's most interesting topics. So whether you're interested in blockchain privacy, scalable computation, or just love elegant maths and cryptography like I do, then gather round and welcome. Zero-knowledge proofs are transforming how we think about privacy and verification, and by the end, you will understand what they are from a high level and why I think they're really, really cool. Let's start with a very simple scenario. Imagine you have two friends. Let's call them, as we always do, Alice and Bob. Alice has discovered that she knows the solution to Bob's very complex puzzle, and she wants to convince Bob that she's solved it. However, she doesn't want to reveal her solution because anyone watching or Bob himself might claim the solution as their own. And this is where zero-knowledge proofs come in. They allow Alice, who we call the prover, to convince Bob, who we call the verifier, that Alice in fact knows the solution, and crucially, without revealing any information about the solution itself. The magic here is that Bob can be 100% convinced that Alice does know the correct answer, but gains zero additional knowledge about what the solution actually is. To create a little definition, a zero-knowledge proof, or ZKP, is a cryptographic method that allows one party, who we call the prover, to convince another party, called the verifier, that they know some specific information without revealing that information itself. Let's give a real-world example. Let's say you are over 18 or over 21 and you want to enter a club. In order to prove your age, you would have to reveal your date of birth. What if there was a way to prove that you are over 18 or 21 without revealing your age or date of birth, without having to hand over any ID? In order for a zero-knowledge proof to be valid, they must satisfy 3 fundamental properties. And we're going to go into these in a little bit more depth in a different video, but I'm going to summarize them now from a high level. The first one is completeness. If the statement is true, an honest prover must be able to convince the verifier. The second one is soundness. If the statement is false, no dishonest prover can convince an honest verifier, except with maybe a teeny, weeny, tiny probability, but we're going to ignore that for now. And third and finally, of course, it must be zero knowledge. The verifier, or anybody else for that matter, must learn nothing except that the statement is true. There's a lot of different terminology that we're going to go into in a different video, but I just wanted to take you through a few of the use cases. Since blockchains are inherently transparent, we need a way to also include privacy of our data and information, such as wallet balances. We need to enable scalability without compromising on security, enter rollups, and so much more. Zero-knowledge proofs might sound like magic, and they kind of are, but they're based on solid mathematics and cryptography. They provide a system in which we can have blockchain systems which also have an element of privacy and verification. And in the next few sections, we're going to take a little bit of a deeper look into what they are, how they work, all of the different terminology, snarks, starks, plonks, all of this information from a high level. So I'll see you very shortly. There are 2 main types of zero-knowledge proof. The first was an interactive proof, closely followed by the non-interactive zero-knowledge proof. Let's start with interactive proofs since they came first. Here, there's a back and forth conversation between the 2 parties, the prover and the verifier. The most famous example is the Alibaba cave, but for my example, I'm going to call it Patrick's cave. And I want to prove that I know the solution to his little cave puzzle. So Patrick says, "Here lies my cave. There are 2 entrances to this cave, entrance A and entrance B. My cave inside is in fact circular. You can enter through entrance A and exit through entrance B. However, there's a catch. There is in fact a door that lies in the middle of this circular path with a combination code that only I, Patrick, know this. Actually, I should be saying this in a lower voice. Only I, Patrick, know the solution to. You do not know the solution to this door combination code." And then Ciara says, Patrick, you have forgotten. I am in fact a witch because I went to Hogwarts and I do know the solution to this combi code on that secret locked door. And then Patrick says, "Prove it." And I say, "Okay, give me a puzzle and I will fix it and I will show you." And then Patrick says, "I know how to figure out if you know the solution. What I'm going to do is turn around. You are going to enter through an entrance. I don't know which one. And then I'm going to tell you which door to exit through." So Patrick turns around. Ciara enters through entrance A. Patrick says, "Exit through entrance B." She enters the combi code. She runs through. And she exits through entrance B. Patrick is not convinced. He says, "How do I know you didn't just enter through entrance B and exit through entrance B?" And Ciara says, "I guess it's a 50-50 chance. We'll have to repeat this a number of times until you are fully convinced that I do in fact know the combination code." So Patrick turns around again. Ciara enters the cave. He turns back around to see that she has in fact entered the cave. And he says, "Exit through entrance A, please." And then she exits through entrance A. He's still not convinced because there's 25% chance that she just went through the right side both times. So they repeat this again and again and again. And Ciara gets it right every single time until finally Patrick says, "You know what, Ciara? I am convinced you did go to Hogwarts and you are a witch because you do know my combination code. Either that or you saw it written in my EMV because I'm a loser and I write my private information in EMV files." And this is a tale as old as time. And it is in fact an example of an interactive zero-knowledge proof. It's called interactive because there are multiple rounds of communication between the prover who was Ciara in my example, and the verifier, who was Patrick. But these types of proof are extremely time consuming, and these repeated interactions are not practical for blockchain applications because we need to maintain the state between the different rounds. So we'd have to store this information, and only Patrick would be convinced that I do in fact know this combination code. If I wanted to prove to someone else I knew the combination code, I would have to go through this whole process again of having to convince them with multiple rounds, which would be extremely time consuming and annoying. And this is why we use non-interactive zero-knowledge proofs, where there is only one round of communication. And this involves sending a single message from the prover to the verifier and contains all the necessary proof information. And the verifier can check the proof independently, and they can be verified by multiple different people, thus enabling trustless verification suitable for blockchain applications, which we can integrate into smart contracts and decentralized protocols. One way I like to imagine non-interactive zero-knowledge proofs is with the famous Where's Wally example. This isn't really an example of a non-interactive zero-knowledge proof since they're actually mathematical, so algorithmic, funky math stuff, but they're a nice way to visualize what's going on. So I have a Where's Wally puzzle, and I say, I know the solution. I know exactly where Wally is, but I don't want to tell you the solution. I don't want to tell you where Wally is. So I could do a couple of things. I could photocopy the image. I could cut out Wally's head and give it to you and be like, hey, here's Wally's head. I could only do that if I knew where Wally was. The other thing I could do is get a really large piece of paper, so large that you can't even see the underlying piece anymore. I could cut a little hole and then align it so that you could see I knew exactly where Wally was. And you would be fully convinced that I knew, in fact, where Wally was without revealing to you exactly where in the picture he, in fact, is. There are many different types of non-interactive zero-knowledge proof, including snarks, starks, bulletproofs, and these are actually umbrella terms. For instance, snarks encompass both Groth16 and Plonk, but these are all just different types that work in different ways, using different cryptographic methods. We will go into these and their differences a little bit later. By using non-interactive zero-knowledge proofs, we have enabled lots of different use cases, such as verifiably proving your identity or your age, proving your balance is above a certain threshold, verifiable computation in a blockchain, and so much more. Before we continue, I think it's important to define some terminology that's going to be used throughout this course and also future ZK courses on Updraft. So if you're going out into the wild to do your own research on ZK proofs, then you'll understand what these terms mean. I think it's important to point out here that although I am going to define these terms, not everyone uses these keywords in exactly the same way. Sometimes it depends a little bit on the context, and there is some disagreement on the exact definitions. So in some circumstances, there may be a little bit of variation. You're not going to find full consistency everywhere. Regardless, it's still important to understand what these keywords mean before you see them being used out in the wild, and in order to understand what they mean depending on the different contexts. So the first keyword is claim or statement, and often these words are used interchangeably. A claim or statement is an assertion that something is true. In the context of zero-knowledge proofs or ZKPs, it refers to the property being proven without revealing any additional information. An example of such statement or claim is I know a number x such that x to the power of 2 equals to 9. This is the statement or claim that the prover wants to prove to the verifier without revealing x. Another example could be I am over some minimum age, therefore I can enter your adults only club. The prover needs to convince the verifier that they are over the minimum age without revealing their age or date of birth. So to summarize, the statement or claim is the thing that the prover is proving to the verifier that they know without revealing any additional information about what it is that they know. Next up, we have private and public inputs. An input is like a variable to your zero-knowledge proof system. This is going to make a bit more sense as we go on, so bear with me for a second. So in a zero-knowledge proof system, inputs can be categorized two ways. First of all, private inputs. These are values in the system that are only known to the prover and not the verifier or anybody else. For example, passwords or secret keys, and these are part of something known as the witness, which we're going to define shortly. This is, as usual, most easily understood through an example. Let's return to our original examples. In the statement, I know x such that x to the power of 2 equals to 9, x is an example of a private input. Or for the claim, I am above some certain age, and therefore I can enter the club. Your age is an example of a private input. The second type of input is a public input. And as this sounds, this is a value that's known by both the prover and the verifier. And it's used to check the proof's validity. This can include things like commitments, a public key, or a hash digest. But again, this is best explained using an example. The first example doesn't have a public input, but the second example could. I am above the threshold age and therefore I can enter your club. The public input could in fact be the minimum age, 18 or 21, etc. This could be an example of a public input that's known by both the prover and the verifier. The next keyword is a constraint. This is a mathematical equation or condition that must be satisfied for the claim to be true. The constraints define the rules the inputs must follow to be valid. Exactly how they are expressed depends on the specific constraint system. I'm going to touch on this from a very high level, but don't worry too much about proving and constraint systems. Again, let's return to our examples. So for the claim, I know x such that x to the power of 2 equals to 9. The constraint could be assert that x to the power of 2 equals to 9. The specific structure of this constraint depends on the specific proving system. For example, in an R1CS proving system, this could be broken down into intermediate steps, where we first say that x times x equals to an intermediate value z, and then z minus 9 must be equal to 0. And this specific structure is used in the R1CS proof system. And this is exactly the same as saying that x to the power of 2 equals to 9, but it's just broken down into an intermediate step. Don't worry about this though, because in most instances when we are writing constraints, this is abstracted away. So you don't need to know too much about this. I just wanted to touch on it very briefly. Let's return to our second example. I am over the minimum age and therefore I can enter the adults only club. The only constraint would be that we would require that the age is greater than or equal to the minimum age. So there are multiple types of constraint systems that dictate how these mathematical rules and assumptions are structured, like Plonkish constraint systems or R1CS, but most of the time these differences are abstracted away. For example, if you're writing your zero-knowledge proof program using a language like Noir or Circom. Next keyword is circuit, which you might have heard already in the context of zero-knowledge proofs, but what actually is a circuit? A circuit is a system of these constraints. So it's represented as a series of mathematical relationships and operations. The circuit defines how all of these constraints work together to verify the claim. So all of the constraints together need to pass to convince the verifier. Let's return to our second example. So for our first example, we could only have one constraint. So therefore, our circuit is in fact just this one constraint. In our second example, I am over the minimum age, therefore I can enter the club. Perhaps we also want to have a maximum age. I am over this minimum age, but below some maximum age. Therefore, we would have two different constraints. These two different constraints together would make up the circuit in this example. The next keyword, which we've mentioned already very briefly, is a witness, which again, you might have seen out in the wild when reading up on zero-knowledge proofs. A witness is the set of secret values that allow a prover to demonstrate that a statement is true. It does include all of the private inputs, but it could also include intermediate values computed during proof generation. So it's just all of the information that the prover needs in order to prove that their initial statement is true. The witness must satisfy the constraints of the circuit to ensure that the claim is valid. In some instances, such in Vitalik's QAPs blog, the witness refers to the assignments of the variables in the circuit. For example, for the claim I know x, such as x to the power of 2 equals to 9, the witness could be x, but in some examples, it could include intermediate calculations such as x to the power of 2. Finally, now that we have defined all these other terms, let's redefine the prover and the verifier using this terminology so that we get used to things. So the prover, as we said before, is the entity that generates a proof by demonstrating knowledge of the witness while satisfying the circuit constraints. The prover does not reveal the witness, but still convinces the verifier of proof of computation, and this enables them to prove that the statement was initially correct. So they can prove that their inputs satisfied the constraints, and then they can prove that this computation was successfully performed. The verifier checks whether the proof is valid. Given the proof and inputs, the verifier runs a verification algorithm to confirm whether the prover's claim is true without revealing any additional information. This verification could be done off-chain, or a verification smart contract could be generated in order to verify the proof on chain by anyone. So that was just a whistle-stop tour on different ZK terminology. If you found any of this confusing, don't worry too much. Just make sure that you keep reading blogs, keep watching videos, rewatch this video in order to get familiar with this terminology, because it is difficult. There's a lot of nuance here. So the more you surround yourself with the information, the easier you're going to find things. There is one final piece of terminology that I want to define, and that is the trusted setup. This is going to be a little bit longer as there's a bit more information you need to know here. So in the next video, we are going to go into the trusted setup from a high level. What is the trusted setup? The trusted setup is a crucial step in certain ZKP systems, particularly in snarks like Groth16 and Plonk, which are examples of specific types of snark. Understanding what the trusted setup is from a high level is essential for grasping how these proofs remain secure and efficient. And by understanding what the trusted setup is, it enables you to be able to understand comparisons between different ZKP systems, like different snarks and also starks. So what actually is the trusted setup? To quote Vitalik, a trusted setup ceremony is a procedure that is done once to generate some data that must be used every time some cryptographic protocol is run. So a person or a group of people have to create some secret to generate this data. Once the data has been generated, the secrets must be destroyed. It is the initial step in generating a zero-knowledge proof where cryptographic parameters are created. These parameters must be securely generated, as any compromise could jeopardize the security of the entire system. There are some key concepts associated with the trusted setup that I'm going to walk through now. Initially, we have something which is referred to as toxic waste. During the trusted setup, random values are generated. If these values are leaked or compromised, an attacker could forge invalid proofs that would pass verification. In order to maintain security, these random values must be securely destroyed. Next, common reference string, or CRS. This is a set of public parameters that both the prover and the verifier use in the proof generation and verification process. And this is the cryptographic parameter that is created during the trusted setup. Next, we have structured reference string, or SRS. And this is a specific type of CRS, but instead it contains structured data with a specific format. For example, elliptic curve points. So points on an elliptic curve, where these points are derived from a secret value. For example, you could generate a secret value tau. This is an example of toxic waste. And the SRS would be some generator point, a point on the elliptic curve used to generate the other points, with different powers of this tau. You don't need to know what this generator point is. You just need to know that the SRS is structured data and in some instances uses this secret toxic waste value tau, which we're going to return to shortly. Next, we have multi-party computation, or MPC. This is used in lots of different instances, but specifically, we're referring to MPC in the context of zero-knowledge proofs. And this is a security-enhancing process, where multiple parties sequentially contribute to creating a final parameter, such as tau. Each participant receives the current parameter, their own secret transformation, they contribute a tiny bit of randomness, and then they pass on this parameter. They then destroy their contribution. The security comes from the fact to reconstruct the final random value, it would require all participants to keep their secret. So that means that even if there's only one honest party that destroys their contribution, the secret cannot be reconstructed and the system remains secure, regardless of whether some parties were malicious and kept their contribution. Think of this a bit like a chain of locks. If one person in the chain destroys their key, the full chain can never be unlocked. Even if everybody else kept their keys, there would still be one lock. We've touched on briefly one specific type of trusted setup, and that is the powers of tau. And this is used specifically in snarks like Groth16 and Plonk. The powers of tau is a series of elliptic curve points generated using a multi-party computation. It's called the powers of tau because each of these elliptic curve points are created by some secret times the generator point. So tau to the 0 or 1 times g is the first elliptic curve point, tau to the 1 times g is the second one, tau to the 2 times g is the third one, and then so on. Crucially, by using a multi-party computation, no one ever needs to know tau. There is a separate multi-party computation that happens for each elliptic curve point, which you'll be able to see in the graphic here. So pause if you want to understand how this works. But essentially, each person is contributing their own randomness guess their own value of tau, which all collectively come together to create this tau, which cannot be calculated unless you have every single person in the multi-party computation's contribution. The trusted setup could also include something called a polynomial commitment. And this is a cryptographic method that allows you to commit to a specific polynomial while keeping the coefficients of this polynomial secret. And this allows you to prove properties of this polynomial later. Different proving systems use different commitment schemes. For example, one type of specific polynomial commitment scheme is the KZG commitment. Essentially, a polynomial commitment is a way to say, this is the polynomial that I am going to be using, without revealing the coefficients of said polynomial. Let's go through some trusted setup examples. And here we're specifically going to be focusing on snarks, as they require a trusted setup. So trusted setups can either be circuit specific, meaning that they need to be regenerated for every specific circuit, or universal, meaning they can be reused for different circuits. So Groth 16 is an example of where the trusted setup needs to be circuit specific. It is a two-phase setup. The first phase is the powers of tau phase, where a general purpose SRS is generated for circuits up to a certain size. This part is not circuit specific and can be reused. This is where the powers of tau are used to generate these elliptic curve points. Then we have the circuit specific phase, where the parameters from the first phase are combined with the circuit's constraints to generate a proving key, which is used to generate the proofs, and a verification key, which of course is used to verify the proof. And this is specific to the specific circuit. So this part of the process needs to be repeated for every new circuit. The Plonk trusted setup is an example of a universal setup, where it is not circuit specific. It uses a universal and adaptable SRS, meaning multiple circuits can reuse the same setup as long as they fit within a certain size constraint. Again, we use the powers of tau process to generate an SRS, which is then used for a polynomial commitment. Plonk systems commonly use a KZG commitment scheme, where polynomials are committed using the powers of tau and evaluated at a certain challenge point. So to conclude, the trusted setup is a foundational concept in zero-knowledge proofs, specifically in snarks. It introduces an initial trust assumption, but by using techniques like multi-party computations and universal setups, we can mitigate these risks. Next, let's go through some use cases of zero-knowledge proofs and where they are being used already today in blockchains. There is another important and somewhat confusing distinction I want to make. Zero-knowledge proof of knowledge versus zero-knowledge proof of computation. In our previous video, we introduced terms like circuits and other zero-knowledge proof terminology. Despite the name, zero-knowledge proofs aren't always just about proving knowledge of some secret. More often, they're used to prove correct computation. Prove that I correctly computed these constraints and therefore know the valid inputs. When we talk about zero-knowledge proofs, there's a subtle but important distinction to understand. The term zero-knowledge refers to the privacy property, the fact that you're revealing nothing beyond the validity of the statement being proven. But what exactly are we proving? So thus far, we've assumed that we are proving knowledge of some secret. But in most instances, we're not actually proving knowledge of a secret, but rather we're proving that computation was performed correctly, and thus we know the secret inputs. So by creating a proof of computation, we indirectly create a proof of knowledge of the private inputs. So we're kind of wrapping up this proof of knowledge into a proof of computation. Going back to our previous example, that our age is above some minimum age. Instead of proving the actual age, we are proving that our age is more than some minimum age, 18. We're proving that we performed this computation correctly. Therefore, we must have had the inputs which satisfied the constraints. That's why we use terms like circuits. These represent the computational steps being verified. A circuit is essentially a mathematical representation of a computation with inputs, operations, outputs, etc. The mathematics of the ZK proof was developed to prove the original statement, my age is above some minimum age, without revealing the value. So whilst, yes, ZKPs can be used to prove knowledge of a secret, really what you're doing is proving valid computation and therefore knowledge of a secret. Let's go into a little bit more detail for those 3 requirements for a zero-knowledge proof. First, completeness. If the statement is valid, the proof must always be able to convince the verifier if they have knowledge of the witness. This is a common case for bugs in zero-knowledge proofs, in which the code that defines this zero-knowledge proof is such that a valid input will not produce a successful zero-knowledge proof that passes verification. An example of this could be, I am over 18, and so even though I'm over 18, I do not pass the zero-knowledge proof and I cannot convince the verifier. Going back to Alice and Bob, if Alice is honest and follows the protocol, she should be able to convince Bob. The second one is soundness. So it must be practically impossible to convince the verifier and trick them with an invalid witness. If I'm not over 18, it must be impossible to convince them that I am over 18. Well, 99.999999999% impossible. If the prover doesn't know the information, they can't trick the verifier into thinking that they do. This is another common cause for bugs in zero-knowledge proof systems, in which invalid inputs produce successful proofs that pass verification. And third and finally, zero knowledge. The verifier must learn absolutely nothing about the solution. Only the prover must be able to know the solution to the problem. They cannot extract this data out of the proof itself. And this is, again, another cause for bugs in zero-knowledge proof systems in which this input data is in fact leaked. But through using things like snarks and starks, which are types of zero-knowledge proof systems that have been thoroughly written about and built into systems that you can use as developers, you do not need to write them from scratch yourself. For instance, by using Noir or Circom, you can create these zero-knowledge proofs without having to worry about exposing your inputs. So we've covered how ZKPs are used. How do we actually create one? How are they actually used in applications? In this video, we're going to go through step by step how we use ZKPs practically, breaking it down into the front end and back end components as they're sometimes referred to, and what this means. Generally speaking, a ZKP system comprises of 2 components, the front end and the back end. The front end is the constraint system. It's responsible for defining the problem mathematically. This is your circuit and includes the computations needed to generate and verify your proof. And typically these circuits are written using a language such as Circom or Noir. We'll come back to this shortly. Then we have the back end, and this takes your constraint written in, for example, Noir or Circom. It takes your circuit and generates the cryptographic proofs that can then be verified without revealing the underlying data. But this sounds a little bit up in the air, still a little bit abstract. So let's break this down into steps. Let's start in the front end. So the first step is actually arithmetization. This term sounds scary, but all it means is breaking your problem down into a mathematical form. So for instance, with our example of a minimum age to enter a club, and I want to prove that I'm above this minimum age, it's simply boiling this problem down into the age being greater than or equal to the minimum age. And this process is referred to as arithmetization. So representing the problem itself as a circuit, consisting of those constraints that must be satisfied, where a collection of constraints together is the circuit, which is written with your language like Noir, Circom, or Cairo. And these languages are examples of domain-specific languages, or DSLs. And these languages allow us to describe the circuits efficiently and abstract away a lot of the complexity, which is why you don't need to understand in depth how ZKP math works and things like R1CS and different constraint systems. Instead, you can just understand how the DSL that you're using works. And this is because a lot of these languages compile into ACIR, which is an intermediate representation, which is then processed by the proving backend to create the proofs and verify those proofs. Circom is a bit of an outlier here, as it compiles directly to R1CS constraints. But you don't need to worry too much about that. Once the circuit has been compiled, the prover needs to generate the witness using their inputs. Usually these inputs are inputted into a file, and then the witness is generated using the intermediate calculations required to create the proof. From now on, we will be in the back end. Next, we need to generate the proof. The witness is then used to create a proof of execution. And of course, this is done without revealing any of that sensitive information. This allows the prover to demonstrate knowledge of the correct solution to the circuit without revealing those actual values. So the proving backend processes the circuit representation that your DSL processed your circuits into. So whether that's ACIR or R1CS, as with CIRCOM, it processes this representation and uses the witness to generate a cryptographic proof. And then finally, verification. So the verifier checks the proof against the constraints to ensure that the prover does have knowledge of the correct values. If everything checks out, then the proof is considered valid. The backend can also be used to generate a smart contract, which can also be used to verify the proof as well, if you wanted your proof verification to be on-chain, which in my opinion is super cool. By allowing you to generate a verifier smart contract and deploying it on-chain, it allows anyone to verify the proof, of course, without revealing any of the underlying data. And this is key for things like private transactions or scalable roll-up solutions. So to summarize this video, in practice, ZKPs involve arithmetizing the problem into a circuit using languages like Noir, CIRCOM, and Cairo, then using a backend to generate a proof and then verify that proof either off-chain or on-chain using a generated verifier smart contract. And that's everything you need to know about practical ZKPs from a high level. And uses the witness. Let's go through some real-world applications and some use cases of zero-knowledge proofs to understand why they are so useful and therefore pretty cool. So by now, hopefully you have an understanding from a high level how ZKPs work and what they are. But where do they actually get used? So zero-knowledge proofs actually have a wide range of use cases, both within blockchain systems and outside. They can be used for any sort of privacy-preserving application. For instance, authentication, proving that you have the right credentials without having to reveal your credentials. Think private logins or private identity, ZKKYC. Prove you are who you say you are without having to reveal your government identity. Now, the list of possible use cases outside of blockchains is massive, but I'm going to focus on zero-knowledge proofs within blockchains and their use cases there. So in blockchains, in general, ZK proofs can solve two major problems. That is scalability and privacy. While the inherent transparency of blockchain systems provides many benefits, which by the way, we cover in Blockchain Basics. So if you haven't watched that, then I encourage you to do so. There are many instances where we do in fact want privacy. Maybe I don't want to reveal my exact wallet balance and therefore be vulnerable to attack. Or maybe I have a private vault or a savings smart contract and I don't want people to know the balance of this smart contract. By using zero-knowledge proofs, we can prove knowledge of something without actually having to reveal it. In blockchain systems, zero-knowledge proofs enable both private data in a transparent system, but also provable computation, which helps with scalability. First, let's focus on the scalability part. And this, of course, leads on to L2 rollup solutions, where zero-knowledge proofs are used to verify state changes and therefore improve scalability of L1s like Ethereum. Again, this was covered in Blockchain Basics, so I'm going to do a very quick recap of rollups and why and how zero-knowledge proofs enable this scalable solution. So ZK Sync Ciara is an example of an L2 rollup that uses ZK proofs. So transactions are actually batched off-chain, and then this data is bundled together. And then this bundle of transaction data is then submitted to the L1 for verification. So what they do is they generate a ZK proof that proves the state changes for these bundle of transactions. So instead of having to submit all of the transaction data to Ethereum or the L1, only the proof and the transaction bundle are actually submitted, which drastically decreases gas fees. So actually the transaction information is still transparent. ZK proofs are not being used for privacy. They are purely being used to prove the state changes and prove that transaction inclusion in order to improve scalability and reduce those gas fees. And sometimes these types of rollups are not actually referred to as ZK rollups. They're referred to as succinct rollups, where the transaction data is not kept a secret. There are some instances of private state rollups where ZK proofs are both used to improve scalability and prove computation, but also for private state, such as addresses, balances, etc. An example of one of these types of solutions is Aztec. So moving on from rollups, we can also use ZK proofs to privacy preserve in our on-chain transactions on existing chains like Ethereum. So some applications have been built already that use ZK proofs to keep information secret. One such example was Tornado Cash, which used ZK proofs to mix different users' funds, allowing people to withdraw anonymously. And they did this by breaking the chain between the sender and the receiver. Using ZK proofs for privacy, we can also enable things like private airdrops, private on-chain voting, where you can't see what address voted for what, and so much more. ZK proofs are also being explored for identity verification in Web3. Projects like Polygon ID that allow users to prove aspects of their identity without exposing any unnecessary details. And this is great for things like on-chain KYC without you having to reveal any confidential information on-chain. We've talked about introducing privacy and also scalability to existing chains. What about privacy-first blockchains? Some L1s are built where privacy is at its core. Zcash is a famous example of such an L1. It was launched in 2016 and uses zero-knowledge proofs to enable fully private transactions, where users can choose between transparent and shielded transactions. And this is in fact one of the first examples of a large-scale application which uses zero-knowledge proofs in blockchains. So it's a pretty famous one, hence why I've included it here. And the final example that I want to draw to your attention is bringing web data on-chain, but privately. So let's say I wanted to prove something about some private web data, like my bank balance, but I didn't want that information to be public, transparent, on-chain. But I still wanted to bring that information or proof of that information on-chain. And the way you can do this is actually using a solution by Chainlink called DECO, which is an acronym for Data Enabled Computation Oracle, which allows you to, as I said, prove things about private web data on-chain without revealing that actual data. And this enables you to do things like bring proof of bank details or bank balances on-chain, or verify your age from an official document without revealing your date of birth, and then bringing that proof on-chain in a decentralized way by using the decentralized Oracle network. This enables us to connect traditional web services with blockchains in a privacy-preserving way. Currently, you can only use DECO in a sandbox environment, but I encourage you to play around with it if you're interested. So to summarize, whether it's scaling Ethereum, enabling private transactions, or proving your identity without giving up your privacy, we have no doubt that zero-knowledge proofs are the future and are going to play a critical role in the evolution of blockchains, with the need to balance transparency with privacy. And in the final part of this crash course, we are going to go through from a high level how we can use zero-knowledge proofs in practice. How would someone go about building a zero-knowledge proof into their application, and how does this work? So you have now got to the end of this course of zero-knowledge fundamentals. So hopefully you now understand what a zero-knowledge proof is, the difference between interactive and non-interactive zero-knowledge proofs, so the rounds of communication, the ZK terminology such as provers, verifiers, trusted setups, circuits, constraints, claims, statements, and more. Hopefully you understand the fact that zero-knowledge proofs have to have zero knowledge and what that means, completeness and succinctness. And then we have seen some example ZK projects and how ZK projects are actually structured. Now, of course, if you have any questions, please drop them in the GitHub discussions tab associated with this course, or ask your favorite AI agent, because this knowledge is going to take a little bit of time to really solidify. And now you have the foundations that you need to be able to learn more, to be able to go and build your own ZK projects or learn more in depth how the math works. So stay tuned. Thank you so much for watching. If you have enjoyed this course, then please let us know on Twitter by tagging me at Kieran Nightingale or at Cyfrin Updraft, or both, and let us know that you have finished this course and that you enjoyed it. And if you have any feedback, then please let us know. And I will see you very shortly in the next one. Goodbye.